Can go.
Right. Thank you, Professor Lola, for inviting me in your department to present this my research paper entitled Nonparametric Analysis of Random Coalitional Utility Models. I'll start by saying that I'm a PhD student at Western University in the Department of Economics, as you can see here. So this paper is basically about microeconomics, but I use some statistical tools. So as a first motivation, random utility models are models of stochastic choice, which aim to model individual choices among alternatives. The term randomness here simply means that only an analysis of the probability of choosing one alternative over another is possible. In the literature, random utility models have allowed to explain whether the distribution of choices observed for a population of consumers is consistent with rational choice theory. So rational choice theory in microeconomics simply means that consumers behave as utility maximizers. So another usefulness of random utility models is that they allow to analyze, they are good for analyzing demand and welfare change in the presence of unobserved heterogeneity. So in a recent paper, Kitamura and Story provided a statistical test of ROM that accounts for sampling uncertainty in cross-sectional data based on the axioms of McFadden and Richter. So in that model, individual rationality is characterized by the generalized axiom of revealed preference. And in microeconomics, the generalized axiom of revealed preference always requires that transitivity of preferences is satisfied. And what is transitivity of preferences? Basically, if you have three items, X, Y, and Z, the transitivity simply means that if you prefer X to Y and Y to Z, then you will necessarily prefer X to Z. However, the paper of Kitamura Stoye has been tested. The model has been tested on consumer expenditure survey. But as we all know, it's difficult to check or verify transitivity on consumer expenditure survey. Also, the empirical literature has regularly documented violation of transitivity of preferences. Experimental evidence against transitivity of preferences are, for instance, Luch, 1956, Tversky, 1969, and a recent paper by Kwa. So one example of non-transitive revealed preference is the Condorcet paradox in game theory, basically where a voter chooses between pairs of candidates in a way that cycles through candidate. So basically the transitivity fails. There is also this recent paper by Chechin and Demerck, who shows that in the Spanish consumer survey, at most 30% of consumers were not satisfying transitivity. So given that transitivity does not hold in practice, or does not hold always, and given the importance of random utility model, it is important to think of a novel model of ROM that can be robust to deviation from transitivity and address the issue of transitivity shown experimentally. So if we assume, for instance, to relax the transitivity assumption from the Kitamura and Story framework, then individual rationality will not be well defined, simply because utility functions will no longer represent preference relations as we know based on Arrow-Debreu theory. According to the Arrow-Debreu theory, a preference, a utility function represents a preference relation if and only if that preference relation is transitive and complete. So relaxing the transitivity, basically, we will have to think of a new way of modeling individual rationality. So thanks of the works by Agia et al. And Nishimura and Oke, who shows that If a binary relation is non-transitive, we can represent, we can think of a preference function that would represent that binary relations. In fact, a preference function in this setting is just a map. I mean, the preference function maps all the pairs of commodity bundles to real numbers. And in this framework, instead of having a utility maximizer, we are going to have a consumer who maximizes a preference function. So basically, combining this new notion of individual rationality to the framework of Kitamore's story will make it possible to develop a novel model of stochastic choice that is robust to deviation from transitivity of preferences. Moreover, with such a model of stochastic choice, one can analyze demand and welfare change in the presence of unobserved heterogeneity. So, what is the research question in this paper? So, suppose an econometrician has a repeated cross-section of demand and price data. Can we decide if the data could come from a population of rational consumers with complete but not necessarily transitive preference relations? So the fact that I put not necessarily transitive is because I would like to develop a model that is free from transitivity. So the model will be the model will account for whether consumers have transitive preferences or not. Now, the second question is, in the case where the data came from a population of rational consumers, can we quantify the fraction of consumers who are better off because of a price change? That's another question. So to answer the research question, I study a population of consumers that satisfy the weak gap. The weak gap is a weaker version of the gap that I introduced in the first slides, and it has this advantage that it allows for non-transitive behavior. And Agia et al. Proved in a paper that the weak gap is empirically equivalent to the coalitional multi-utility preference function. In fact, coalitional multi-utility preference function is a specific type of preference function. In fact, the weak gap cardinal rationalizations in the paper by Agia et al. Use a CMU maximum representation with a coherency restriction in coalitional structure. And the CMU representation aggregates multiple rationals without preference reversal that allow for transitivity violations. So based on this work by Agia et al., I provide a new characterization of CMU models when we observe a cross-section of choices made by heterogeneous households. In fact, in the paper by Agia et al., the paper do not take into account taste variation among consumers. So the new characterization of CMU model that I developed in this paper take into account heterogeneity and taste variation. So now regarding the contribution in the literature, I developed a new characterization of CMU model when we observe a cross-section of choice. So this result connects to the literature on stochastic reveal preference testing. I also developed a novel model of random utility model that is robust to deviation from transitivity of preferences. I also do a welfare analysis based on the new stochastic choice, and this welfare analysis is also robust to deviation from transitivity of preferences. And this result connects to the literature on welfare and counterfactual analysis on the unobserved heterogeneity. Also, the result also connects to the literature on partial identification, because when I measure the proportion of consumers who are better off due to a price change, is basically a problem of identification. So last but not the least, I illustrate my result by using the UK Family Expenditure Survey, and I show evidence against wrong why my random CMU model is not rejected by the data. So I'm going to define what is a weak gap. I'm going to tell you what is a preference function, and then I will tell you what is a random coalitional multi-utility model. So we are going to suppose that consumer buys the bundle YT belonging to X. So YT is a bundle of goods, X is the set of alternatives. So L is greater or equal to 2 groups. So we work, so the framework, in the framework, we work for more than 2 groups, 2 dimensions. And in each period, PT is the prevailing price. So YT, RD, YS, as you can see here, simply means this. So that's the condition. So YT is directly within preferred to YS is if PTYT is greater or equal to PTYS. PTYT is basically how much you spend to get YT. And basically PTYS is how much you spend to get YS when the prevailing price is PT. Now, what is the weight gap? The weight gap simply means that if I have a sequence of observation based on price PT and quantity of goods in each period, I will say that the sequence of observation obey the weak generalized action of revealed preference if there is no pair of observation in which if YT is directly really preferred to YS, we have YS directly really preferred to YT. Now, as I defined in the second slide, a preference function which we are going to use now to represent a non-transitive binary relations. So a preference function maps all the pairs of commodity bundles to real numbers. And I'm going to say that R of YTYS is greater or equal to 0 if YT is preferred to YS. And R of YTYS is strictly less than 0 if YS is strictly preferred to YT. Now, instead of working with the preference function, which is very big and which span a very big category of function of 2 arguments, I'm going to impose some restriction on the preference function. And this restriction that I'm going to impose is what will help me characterize the weak generalized action of the preference. So instead of working with the general preference function, I'll work with a maximum preference function. Basically, the CMU preference function will be defined as R of YTYS, which is equal to max of U, capital U belonging to omega. Capital U here is a set of attributes. So an attribute can be the color of the good, the quality of the good, the taste of the goods. And then the little u here are the utility functions. So each attribute has some utility functions, and this is the difference. So basically, that's how I define the CMU preference function. So capital omega is a compact set, and U is a compact set of piecemeal utility functions. So CX is a matrix space relative to the submatrix defined as follows. So I will say that the preference function is coherent if whenever you take 2 attributes, the intersection is always non-empty. Now, a question that you guys can ask me will be, okay, why do you think that this new representation of the binary relation really catch the notion of non-transitivity? In fact, if I have 3 good x, y, z, the fact that R of xy is greater than 0 and R of yz is greater than 0 does not provide me any implication of the sign of R of xz, because I can have R of xy equal to 1, R of yz equal to 1, but R of xz equal to -1. So representing the preference relation with R and with R defining with multiple utilities is truly a representation that admits non-transitivity. However, if the preference function is equal to a single utility U, then the preference function R will satisfy transitivity. Why? Because if R of xy is greater or equal to 0, R of y is greater or equal to 0, if we have only a single utility, proving that u of x minus u of z is greater than 0 will be, it's easier to prove, basically. Any question? Any question, please?
Oh, that's tough now.
Okay, so this theorem is a result by Agia et al., which say that if I have a data set that obeys the weak generalized axiom of the real preference, then the same data set can be rationalized by a coherent CMU preference function, which is asymmetric, continuous, monotonic, and piecewise concave. So for the definition of asymmetric, continuous, and monotonicity of the preference function, I can just take you there for those who are interested. These are the definitions, but I'm not going to spend much time here, so I will proceed. So let's give an example of a preference function. What is a preference function? Consider three goods. Let's say an hamburger, a pizza, and a hot dog. Assume preferences consist of two attributes. So attribute here, the first attribute is whether the good is healthy or not. And then the other attribute is whether the good is tasty or not. So let's assume that consumers are endowed with the three reference dependent utilities as follows. UTT, which is the utility for the taste. UHH is the utility for whether the good is healthy. And UTH is basically a utility that combines the two, so healthiness and tastiness. So we can rewrite the CMU preference function as a maximum as follows. And in this example, attributes UT are UTT, U star TH, UH are UHH, U star HT. Remember, utilities are is a set of piecemeal utilities. So the piecemeal utilities are this one then. I'm going to go to a second example. So consider a consumer who has two attributes, UC and UD. Let's suppose that U1C, U2C, U are the utility functions that belongs to attribute UC, and UD and U are the utility function that belongs to the two good X and Y, and I assume that consumers' choices are described as follows. What are you going to observe? First of all, this preference function is coherent. Why is it coherent? Because the two attribute has a common piecemeal utility, which is capital U. In the previous example, the preference function was also coherent because UTH, which is equal to UHT, was part of the two attributes. So how do I define whether the consumer prefer Y over X? In fact, what we can see here is that in one attribute, which is UD, the consumer ranks Y higher than X. So basically all the piecemeal utilities in UD recommend Y higher than X. Because of that, R of YX is strictly greater than 0. In other words, R of YX is strictly greater than 0 if there exists an attribute in which every utility recommends Y higher than X. So now, having defined the preference function, I'm going to develop now the stochastic version of it and show you how to rationalize with a random CMU preference function. Given that I'm talking about random preference function, I need to first of all define a probability space. So let theta, F, and mu be a probability space. So theta is in this framework is the set of types. F is the sigma algebra, and mu is a probability, as we all know. So I define the random CMU preference function as a measure mu over the set of all locally non-associated CMU preference function. So given L, a patch in this framework, we are going to hear these words a lot. So a patch is basically a subset of a budget. So in economics, we work a lot with the budget constraint. So the budget constraint is basically a set that gives you the relationship between how much you spend and how much you have in your pocket. So in this framework, I will assume that the budget can, because I'm doing an analysis on several periods. So you can have budget in period 1, budget in period 2, and the budget here, as I define, if you are in dimension 2, the budget is a line. If you're in dimension 3, the budget is a plane. So this is how I define the budget. Now, the choice in this framework, C of Y XLT, this is the event where the consumer choose a commodity bundle Y that falls within the patch XLT. So it is defined this way. And then pi KT is basically the probability that some set of consumers choose the patch XLT, which is a subset of the budget BT. So there is an important difference to do here. What I was showing previously, the weak gap and the CMU preference function, I was showing you how I characterize individual rationality. So at the individual level, a consumer chooses a bundle that falls within the patch. But then my analysis at the population level will use an aggregation of demand. So basically what happened is that at the population level, I suppose there exist a representative consumers. And so these representative consumers picks a patch within a budget, which is what I'm going to explain here. In each period, each consumer picks a bundle of goods that falls within a patch. At the population level, we consider a representative consumer, representative in the sense that the guy has the same characteristics. So for instance, I may have many consumers who choose on a particular subset of a budget. So those set of consumers will be represented by a representative consumers who has the same characteristics as those consumers who choose within that patch. So I'm gonna give two assumptions. One of the assumptions is monotonicity, like more is better. So if I have two commodity bundles, if one commodity is greater or equal to another one, then my preference function will be greater under X than under Z. As you can observe here, the monotonicity only applies on the first argument of the preference function. So the other assumption that I'm going to propose here is that if I'm doing a two-period analysis, if the budget overlaps, I'm not going to consider points that belongs to the intersection of the two budgets, because my goal is to compare choices in period T and in period S. So if the choice in period S is equal to the choice in period T, basically there is nothing I can say. So I'm not going to consider those points. Again, I'm also I also suppose that all consumers' coherent CMU preference function are drawn from the same collection of coherent CMU preference function. So basically here I'm trying to say that there exists a population of coherent CMU preference function, and then all the CMU preference function that I'm using are drawn from that population set of CMU preference function. Now, given that I'm doing a comparison at the population level, basically, as I said, at the population level, a representative consumer choose one patch over another. So I'm going to give a criterion to compare patches. How do I compare two sub-budget of a budget? So given TL, the patch XKT will dominate the patch XKL, and I denote it this way if this condition hold, where YT and ZL are respectively the representative commodity bundles on patches XKT and XKL. Basically, why do I use the word representative commodity bundles? In fact, given the the rationality the rationality result that I'm using here. So the weak generalized axiom of revealed preference, it turns out that if I have two budgets, right? So every commodity bundles on a patch will give the same directly revealed preferred result. So basically, if I choose a commodity bundle Y on XKL, if it is directly revealed preferred to any other commodity bundle Z on XKT, for instance, then this will be the case for all other commodity bundles on XKL. So that's why instead of using all the points, I will just work with a representative consumers or with a representative commodity bundles. So now, this is the most interesting part of this presentation. So if instead of observing prices and the quantity of each goods over a certain period, I observe pi t, which is the distribution of choices and the prevailing price at period t, how do I rationalize such a data set? Remember, here I gave you a result on how to rationalize a data set when the data sets are of the form OT equal PT YT. So YT here is the quantity, PT is the price. So I told you, if the data set obey weak gap, then we can find a preference function that rationalizes the observation. So this is basically the deterministic version. Now in the stochastic version, where instead of the quantity we observe the probabilities, one question that we can ask is, how do we rationalize this type of data sets where we have prices in each period and the probability? So the pi t is a collection of probabilities or probabilistic choice that describe the observable distribution of consumers' demand over the budget BT. So how do I rationalize this? The intuition is as follows. To rationalize S, one needs to find a distribution on the family of coherent CMU preference functions that generates a demand distribution at each budget set corresponding to what is observed. So if I consider, for instance, a two-period observation, so a rationalization by the random CMU model will involve that the observation in period T match with observation in period S, such that the pair YT theta, YS theta, along with the associated price, obeys weak gap. And more generally, that's the formal definition, I would say that S is rationalized by random CMU model if there exists a probability space and a random variable Y, such that almost surely this data set can be rationalized by a coherent CMU preference function that is asymmetric, continuous, monotone, and piecewise concave. And how am I going to define the choice probability? When I know mu, the distribution that rationalizes the data, pi t y is equal to the measure of this set. Now, having defined this is just a formal definition. As a statistician or economist, I need to have a testable condition, a condition that I can take to the data. With this definition, I cannot do anything. So basically, in the next slide, I'm going to show that this definition is equivalent to a condition that I can take to the data. And so the empirical content, I'm going to say that S is rationalized by the random CMU model if and only if the discretized choice probability pi satisfy the following condition. In this definition, A is a rational matrix. So each column of A is a vector representation of a given rationalizable non-stochastic demand system. The pi is a vector of choice probabilities. So saying differently, this condition also implies that if S is rationalized by the random CMU model, then the choice probabilities is equals to the mass of weak-gap consistent types. I'm going to show you this with an illustration. I will take two budgets and two dimension, and I will show you how rationalization implies that choice probability is equal mass of weak-gap consistent type. Now, something to precise in this result is that this theorem is similar to the theorem of Kitamura and Story. The difference between his condition and mine is that my rational matrix has more columns than DS. More columns because given that I am relaxing, I'm allowing for transitivity of preferences, I have more columns because the columns represent the rational types. So the set of consumers that obey rationality. So this matrix is the same in terms of rows as the matrix of Kitamura and Stoye, but I have more columns than Kitamura and Stoye. Also, this theorem is a generalization of Kitamura Stoye if the preference function is defined with a single utility function. Now, illustration with two period to good. This is budget 1, this is budget 2. I assume that the budget overlaps. So X01 is this patch, X11 is this patch. So basically, a consumer in period 1 will choose a commodity bundle Y, which is Y1 and Y2. And this commodity bundle may fall here. If the commodity bundle falls on X11, then we are going to say that the consumers have chosen the patch, the representative bundle falls with X11. It may happen that the commodity bundle falls on X01. Also, in period 2, we may have consumers who choose a commodity bundle that falls within X02 or X12. So basically, the X01 and X02 are the subset of the budget. Now, at the representative level, in period 1, the representative consumers will either pick X01 or X11. And so pi 01 will be the probability of choosing the patch X01, and pi 11 will be the probability of choosing the patch X11. So if I want to define the probability, the choice probabilities, it will be defined as follows. Now, in these examples, what are the rational types? In this example, we have 3 rational types. So X01, X02 is a rational types in the sense that if you pick a commodity bundle on X01, that commodity bundle will be directly preferred to a commodity bundle on X02. So this is a rational type, X01 union X02. X11 union X12 is a rational type. And then we have a third rational type, which is X01, X12. So the condition, so we are going to say that this data set is rationalized by the random CMU model if and only if there exists this vector such that we have this condition. In the case of 2 good and 2 budget, this is how the matrix looks like. So the first column of this matrix corresponds to a rational type, which is basically this one, X01 union X02. So this triangle or this angle, X01, X02, this will capture a rational type in the sense that we assume that the consumer chooses here with the probability of 1, and here with the probability of 0, here with the probability of 1, and here with the probability of 0. Basically, that's why we have this. And the fact that we said this condition is equivalent of saying that the probabilities are equal to the mass of weak-gap consistent type is basically this result. And what I'm saying next is that this condition AV equal P is a non-parametric condition. Non-parametric in the sense that we don't need to know what is the random CMU preference function of a representative consumers. That's the advantage of the non-parametric analysis. So I don't care about the properties of the random preference function. This condition is non-parametric. I can take it to the data. So I can test it statistically. And because I want to test it statistically, I need to define what is my null hypothesis. So my null hypothesis here is that the sample of cross-sectional demand distribution could have been generated by a population of rational consumers. So now, the previous hypothesis testing, the previous hypothesis is equivalent to this result, where epsilon is a positive definite matrix. In the data, when I bring this to the data, I can choose epsilon to be the identity matrix. So the test statistics looks as follows, where pi hat, it's an estimate of the choice probabilities. So in this work, given that it is based on Kitamura and Stoye's paper, what I did was that I used the bootstrap procedure explained in Kitamura and Stoye to compute the critical values of my test. And if neta is equal to AV, so basically if AV is equal to pi hat, then GN, which is the test statistics, is equal to 0, and the estimated choice probabilities are stochastically rationalizable. So I'm not going to explain too much how I simulate the critical values, but if there is a question later on, I'm going to show you. I have it here. So next, I have the expenditure function. Basically, why do I do the expenditure function? Given that I want to do a welfare analysis on the observed price change, I need to basically define how expenditure minimization is in the framework of non-transitive preferences. And in the non-transitive preferences, it follows that we can define expenditure minimization as follows, where AZ is defined as this set. Now, this theorem is a result that I have, but I'm not going to elaborate too much on it. So, having this theorem, I define what I call the direct compensation function, which is the minimum amount of spending necessary at price P to buy a bundle of goods at least as good as a given reference bundle Z. So what is the contribution behind this direct compensation function? Is that I prove the existence of a direct compensation function under weak assumptions. In the literature, to have this direct compensation function, people need the preference relation to be strongly convex. Me, I don't necessarily need this. I have a weaker condition than convexity, and I was able to get this result. Now, how do I define preferences between two prices? If I'm saying that a representative consumers prefer price PT over price PS, how do I model that? Basically, PT is preferred to PS if I have this condition. Now, what is the goal of the welfare analysis and price preference? Suppose a government plan to change the sale tax, which may shift the current price from, let's say, PS to PT. So one question we may ask is how to measure the fraction of revealed preferred consumers, the fraction of consumers who are revealed better off at one price relative to another. And to do so, I define this row vector, which I'm going to use later on. The row vector, it's a row vector with length equal to the number of rational types, shows that the corresponding nth element is 1 if the price PT is directly preferred to price PS and 0 otherwise. And more formally, this is how I define the proportion of consumers who are revealed better off at one price relative to the others. Now, this is the welfare proposition. If S is defined this way and is rationalized by a random CMU model, then for every lambda taken in this set, there is a rationalization of S for which lambda is the proportion of consumers who are revealed better off. The same here, there is a proportion of consumers who are better off at PT compared to PS. Again, this is a partial identification. Now, if the matrix A of this condition, the rationality condition, if this matrix A is full rank, then the lower bound is equal to the upper bound, and then the fraction of consumers that we want to measure will be point identified. So this is all for the theory. I'm going to go now to the application. So for the application, I'm going to consider a couples living, because this is a UK consumer survey. So I consider couples living in West Midlands, having one car, at least one kid, more than zero income and expenditure, and were interviewed in the month of January. So I consider 3 goods, and among the goods we have food, non-durable goods, and services. 4 goods includes food, non-durable goods, services, and clothing. So I test both the random CMU model and the ROM on the UK family expenditure survey. So in this table, I first replicate the table 3 in Kitamura and Story. And here, this is the evidence against the ROM. As you can see, for 4 goods, the ROM is the existing model, the random CMU is my model. You can see that my GN, my test statistics, is closer to 0 than the ROM, given the considered consumers. And my p-value, because the p here represents the p-value, my p-value is greater than 0, where here it tends to 0. So basically, when I consider 5 periods and the year 1976, 1980, I see that for the case of 4 goods, the model rejects the ROM. Similar for the case of 5 goods. GN, for the case of 5 goods, you see that the ROM, which is this part, the test statistic is not 0, and the p-value is also 0. So these are some evidence that my model performs better for the considered data set than the ROM. So that's the same here when I consider 3 goods. I have the same results. So the ROM my model perform better than the ROM. So that's all regarding the application. So as a conclusion, I'm going to say that in this work, I develop a novel characterization of CMU models when we observe a cross-section of choices. I also develop a novel model of ROM robust to deviations from transitivity of preferences. I propose a novel measure of monometric utility functions. And also, I develop a welfare analysis that is robust to deviation from transitivity of preferences. And all this being done non-parametrically. Non-parametrically in the sense that I don't care about the random preference of the representative consumers. And as an ongoing a follow-up of this project is to do the counterfactual analysis. The counterfactual analysis basically is looking for sharp bounds for counterfactual discrete choice probabilities. So basically that's what I'm doing next in this project. So with this, I'm gonna close my presentation and I'm open to questions that you have. Thank you.
Thank you very much. Are there any questions from those listening, whether online or here? Fabrice?
Yeah.
Yes, hello.
Yeah.
Yes, please, Wilfried, could you go back to the results from your empirical application?
Oh, empirical application. Okay,
yes.
Here?
Yeah,
Okay.
Your test statistic is JN, right?
Yes.
Okay, and I remember, if I'm not wrong, you used a minimum to define the test statistic. It's a minimum of something.
Mm-hmm.
Yes. Then what about local size and local power? But for now, let's talk about local size.
What do you mean by local size?
like size, but when we are close to the boundary.
Which boundary? Can you be more precise?
Can you go back to your test statistic, please? The definition.
Yeah, that's here.
Your null, sorry.
Mm-hmm.
The null.
Yeah.
Your null.
Each H0 is at the end of the slide.
Sorry?
That's it.
That's it right there at the end of the
Oh,
slide.
yeah, he had a mathematical definition of the null.
That's
it here.
the first line of the next slide.
Okay, yes. Okay. I think I made some chat. I thought it was greater or equal to 0. That's why I was talking about the local size. Okay.
No. That's equal to 0.
Okay, thank you. That's all.
Yeah.
Okay. Any other questions? Now, if I can allow myself a question, I do have a test statistic, and I have a couple of students sitting here with me. And anytime they see test statistic, they want to see a distribution before hearing p-values. So how do you get the p-values in your work?
Yeah, so basically I simulate the critical value to get the GN as follows. So I first of all obtain a 2n tighten restriction of the estimator. Basically, this estimator is it estimates, because I have this condition AV. So this is an estimator of AV. So this solves this. Now I define the theta n tightening recenter bootstrap estimator as follows. And with the bootstrap statistics, I will write the test statistics as follows, and then use the empirical distribution to obtain the critical value for GN. Yeah. So as I said, the object, the neta n here is the true value of pi in the bootstrap population. And it differed from pi hat through the double recentering that we do here. So it's basically a non-parametric approach. Yeah.
Is that clear? Okay. Good, thank you. Anything else?
Please, Fabrice?
I have a question.
Okay.
Right.
It's
Yes.
about,
Oh, sorry.
Go ahead,
me or Fabrice?
please.
Okay. So yeah, good presentation, Wilfried. So I have a question about your application to the data.
Okay.
So
yeah,
you use the same data set as Ketamuria, right?
So basically here, the data set that he used here goes from because the data set covers 1975 up to 1999. So that's what I used to do this replication. But here, I use the period 1976 and 1980. And
In the same data set, right?
Yes, the same data set, yes. And then I consider those couples.
Did you test whether that data set violate the transitivity or?
It's not, I don't think I can do that, because you just observe consumer choice, right?
Yeah, but your framework is like you break the assumption, transitivity assumption, right?
Yes, basically, no, my framework allows for either transitivity or non-transitivity. So if I have a data set